Good morning, everyone. We will do a review session today in preparation for your first quiz. I did put an announcement about topics that will be covered in your quiz number one till the end of the Y delta transformations. So today we're going to go through a few questions and we will hopefully have some extra time to solve any question that you would like to be solved. Um, so at the beginning, I would like to ask you if you have any question. Okay, that was cute. Okay, yeah, thank you, Matthias. Okay, so okay, so back to our session. Before we start, do you have any question about quiz number one? That will be on next Thursday, June 17th at 11:30 a.m. It's going to be for 1 hour. No questions? Okay, so shall we start the review session, or do you have any specific question that you would like me to solve for you? Okay, that's a good question. In quiz number one, we will not have any long answer questions to be written and uploaded. Probably quiz number two, we will have that those types of questions. So, and quiz number one will be a mix. Probably so far it's not finalized yet, but it will be a mix of multiple choices and arithmetic questions where you need to put fill the answer in an empty box. The the total number of the questions is not finalized yet. I may have one bonus question, so I'm still debating and looking at all my options, but that's for quiz number one. Any other questions? Okay, so problem number one asks the following: use Kirchhoff's laws and Ohm's law to find I naught in the circuit shown in the figure below. So here we have the current going into the 10 ohm is I naught, right? Second part, test the solution for I naught by verifying that the total power generated equals the total power dissipated. Okay, so the question here wants to assess my understanding of applying Ohm's law and Kirchhoff's laws. In Kirchhoff's laws, we have the KVL and we have the KCL as well. So in this circuit, as you can see here, we have a voltage source connected in series with this 10 ohm resistor. This doesn't mean that I naught is that voltage divided by 10 ohm. This is wrong. This is one of the common mistakes students do. One of the common mistakes, and I repeat, students do, as they go, well, since I naught is connected in series here, then I naught is 120 divided by 10. This is not necessarily right. Okay. We may have, some other circuits that this could be a special case, but in general, this is not right. This is wrong. If you do this is a major mistake. Yes, go ahead.
Wouldn't the key be you need the entire resistance of the loop to find I naught? So you need the 10 ohm resistor plus the 50 ohm resistor. I suppose minus the 6 amps as well.
You cannot judge it this way that quick. You have to apply the laws and see. Here you have two power sources. One of them is from a voltage type. The second one is from a current type. Both of them are contributing into inducing currents that are somehow distributed in those two resistors, right? So you have first to apply those laws and then find out if what is the portion of the current contributed by each of those sources. So here we want to find I naught using KCL and KVL and Ohm's law. So in this case, if I look at this circuit, I can see that here I have a current going in this direction by this 6 ampere. This is a current source. And I have a current going in this direction, assuming it's in this direction. I will call this one I1 and I will call this one I2, right? So if I am now to write a KCL, so let's assume that here I have my, this is one node, right? This is one node here. So I have, let me call, if I want to call this one A, then I can say KCL at A. It's gonna give me the following equation. I have I naught entering. I have I1 leaving. I have I2 entering equals to 0. Now I know I2 is 6 ampere. So I know I2 is 6 ampere. So if I substitute this in here, what do I get? I get I1 minus I naught equals to I2. I'll move it to the second side of the equation, becomes 6. So I have now my first equation from the KCL. So I have one equation from KCL. Remember, if you count the nodes, you will see that the useful equations here are one equation, okay, which is n minus 1. Here you have two nodes in total, or three nodes in total here. However, I will not try the KCL right here. I will not try the KCL here because it's not going to give me any useful information. Okay, so this is the KCL equation right at A. Now, what else can I get? If I write the KVL equation in here, what do I get? So let me see here. This is, if I write the KVL right here, this is L1. What do I get? So KVL at L1, I have minus 120, so this is 120, right? Plus 10 I naught plus 50 I1 equals to 0, right? So this is a second equation I have now. So I have now two equations, two unknowns. Problem is problem is solved. So the number of the equations should equal to the number of the unknowns in order to solve my my problem. So if I call this one 1 and this one 2, then from 2, rearranging, if I divide by 10, right? So let me first rearrange it. So I have here 50 I1 plus 10 I naught equals 120. If I divide by 10 the whole equation, then this becomes 5 I1 plus I naught equals 12. So this is, excuse my eye here, 3. So now if I add 1 and 3, so adding 1 and 3 gives 6I1. You can put them minus I naught equals to 6, 5 I1 plus I naught equals to 12. If you add them, you're going to get 6I1 equals to 18. And then I1 is 3 ampere. I1 is a 3 ampere. Now, notice what happened to the current. If you just look at I1, I have 6 ampere here coming from this current source. 3 ampere went in here, right? What does this mean? This means that there is another 3 amperes that went toward the voltage source. Now, if I1 is a 3 ampere, then I naught would be using any of those equations. So let me call this one 4. So I can say, substituting 4 and 1. So I have here 3 minus I naught equals to 6, which means I naught is a 3 minus 6. I naught is minus 3 ampere. So the current of the 6 ampere went toward the voltage source. So we found I naught. Test the solution for I naught by verifying that the total power generated equals to the total power dissipated. So in this case, if we go here, we have this. So here, now we have I1. This is, we said I2. So we have I1 as 3 ampere. You have I naught as minus 3 ampere. So in this case, if we calculate this voltage here, call this one V1. Now notice that this V1 across the 50 ohm is also across the 6 ampere, right? So 2nd loop. Why? Okay. So your question is, why didn't we create two loops for this problem? The second loop would have just been 50I2 equals to 0. If you want to create the second loop here, you don't know the voltage across. The voltage across this one is V1, right? So here, what's going to be is basically try to apply the KVL here. I'm just doing it here for you, just to show you. KVL at L2. What is it going to give you? Remember, KVL, we're dealing with voltages. So here, basically, it's going to say minus V1, right? Which is the voltage here, plus V1, which is the same voltage, equals to 0. So if you substitute now here V1 with minus 50 I1 plus V1 equals to 0. So if you, or you're going to call this one V6 ampere, doesn't matter. 6 ampere, 6 ampere, they're the same. But you're going to end up with V for the 6 ampere is indeed 50 I1. I don't know the V6 ampere, so I added I added a variable to my variables. So remember that I don't know the voltage across the current source, right? Remember what did we say about the current source? It can take any voltage. It can take any voltage. So writing a KVL with the existence of a current source is going to add one more variable to me. So this equation did not help me. This equation added a second variable to my variables. I'm looking for the variables that I have already, which are the I naught and I1. I don't want to add, so it did not help me. Does this answer your question? So the second loop is not 50I2 equals to 0. It is 50I2, it is 50I1. It is 50I1 equals to the voltage source across the current source. There is no 50I2 equals to 0. This is a wrong equation. Okay? Okay. Now back to here. So we have those currents, the 3 ampere and minus the 3 ampere, and now we need to calculate the power. So let's start with the resistor here, 50 ohm. So P 50 ohm, as the current is entering into the positive, so it's going to be a positive. We have I1, so 50 times I1 squared, P 50 ohm, is I1 is 3 squared 9 50 is 450 watts. Okay. Now what about the 10 ohm? The 10 ohm, I have the current I naught being negative, but anyway, the resistors will always have a positive power because they always absorb energy. So it's going to be 10 times I naught square 10 I naught as minus 3 and P10 ohm as 9 times 10 is 90 watts. Now, what about the power that is generated by the 6 ampere? Now, if you look at the current I1, the current I1 based on this assumption is positive, which means V1 is as I have put here, right? This is positive. This node A is more positive than this node B, right? So V1 is indeed 50 times I1, and V1 is 50 times 3. V1 is 150 volts. So if V1 is 150 volt, and remember this V1 is also across the 6 ampere, right? So I have here V1 as well. So here is V1 as well. Both. The voltage is the same. The 6 ampere and the 50 ohm are in parallel. So in this case, if I want to calculate the power generated by this 6 ampere, notice that the current I2 is entering, right? The negative. So I have here P 6 ampere is minus the voltage times the current. V1 times 6 P 6 ampere minus 150 times 6 P 6 ampere as minus 900 watts. Now, what about the 120 volt? The 120 volt, I naught indeed is, since I naught is negative, this means that the current indeed is going in the opposite direction. So I have the 3 ampere, I naught is minus a 3 ampere, which means this one is a 3 ampere. Now notice that this current, 3 ampere, is entering the positive terminal of this 120 volt, which means that this 120 volt voltage source is absorbing power. So if I am to write the power 120 volt, if I look at I naught like this, so this is I naught, right? I can say it is I naught that is entering this negative terminal. However, I naught is negative, and that made it positive. So if you look at it from both, if you use both approaches, you're going to get at the end to the correct answer. So if you look at I naught entering the negative terminal, and that's why you multiply it by negative. However, I naught is negative itself, so this is going to fix itself and makes it positive. So in this case, I have 360 watts. So this 120 volt was indeed absorbing power, was not supplying power. So let's put, or let's add them. You should get zero. So if you said power total and you added the supplied and the absorbed, you should get zero. So what do we have here? We have minus 900 plus 360 plus 90 plus 450 watts. So this is going to give zero. And this means the total power supplied should equal to the total power absorbed. Now notice that the 6 ampere is supplying the power. The 120 volt source is absorbing. This is a resistor and this is resistors. Okay. Any question about this problem? I think this problem uh, reviewed all the KVL, KCL, how to apply them, the definition of the supplied power, absorbed power, the conservation of energy, total supplied equals to total absorbed. So it's a very good question with its simple circuit, but still managed to cover all those topics that we have talked about. Any question?
Sure.
Yes.
So I had it backwards, and power absorbed is positive and power put out is negative.
Okay.
Is that correct?
If we have just a second. Hmm. Okay. So back to your question. What's your question, Matthias?
So when power is being absorbed, it's considered positive, but when it's being let out by, let's say, an active source, it's negative.
That's correct. We
Okay.
we always look at the voltage, at the orientation of the voltage and the current. So if the current, so let's assume I've taken this from a circuit just to evaluate the power. So if the current is entering its negative terminal, then I would write it as P equals to minus Vs I naught, right? So this is how I write it. Now, if if I calculated the current I naught and I found that this I naught is negative, so here I have, after I did few calculations, I found out that I naught is minus, let's say, 10 ampere. Vs is 100 volt. Then if I want to calculate the power, then the power for Vs is minus 100 minus 10. This makes it 1,000 watt. Since it's positive now, then this power is being absorbed. This voltage source is absorbing power. You can look at this voltage source, for example, to be a battery, for example, and this battery is absorbing power or being charged, right? If you want to look at the power, you look at it from the power perspective. Does this answer your question?
Oh, yes, thank you.
Okay, you're welcome. Any other questions before we move on? Okay, so the second question is use Kirchhoff's laws and Ohm's law to find the voltage V naught. Show that your solution is consistent with the constraint that the total power developed in the circuit equals to the total power dissipated. So this is the conservation of energy again. So what we need to, so the question is asking us to use those simple laws, Kirchhoff's laws and Ohm's law, to find the voltage V naught and then calculate the power. I guess was the voltage to find the voltage V naught. Yes. So here we have a current controlled voltage source. This dependent source depends on the current IS, which is this current, right? Which is this current. So we need to calculate V naught. So what we know so far is this voltage, 10 volt, is across. Can somebody tell me where shall I start from? I want you to participate if that's possible in solving those problems because this is very good practice to you. Can somebody can somebody tell me where shall I start from? Yeah, you can call it Kirchhoff's laws. I can also call it Ohm's law here. Why? Why I can just say that IS is 10 volt divided by 6. Here
Because
I
there's only
can
one resistor.
because this 10 volt is across the 6 ohm resistor. Because that's 10 volt, this voltage drop, the 10 volt is across the 6 ohm resistor. This way I can apply Ohm's law, right? But in the previous question here, this 120 volt is not across the 10 ohm. Yes, it is connected to 10 ohm from this side, but this one is not connected to the second terminal of the 10 ohm. So I cannot say that I naught is 120 divided by 10, another bigger cross, right? It's not. Here, yes, I can say IS equals to 10 divided by 6 because this 10 is across the 6. Then I can find this current going into the 6. Again, the objective of going and solving those questions is to understand all the tricks and all the hidden things that usually trick most of the students and covers most of the common mistakes done by the students. Okay, so 10 divided by 6, 1.667 ampere. Yes, Matthias.
So IS going into the 6 ohm resistor is 1 2/3 of an amp. But at this little dot here, this node, doesn't it split off into two?
You're talking about the I naught?
No, IS.
IS only goes through the 6 ohm.
Well, I mean, is that there's a node here, doesn't it split in two?
No, no. The only understanding to this node is that they share the same reference point. All of them are on the same reference point. So if you put ground here, this is the ground, this is the reference point for all of them. And don't forget that they are binded by this. They're binded by this controlling variable. That's called IS, right? And that dependent source. You here, you just connect or you have the this point connected to this side or this negative terminal of the voltage source. But in Tinkercad, we don't have dependent sources to show you a demo on Tinkercad. So Tinkercad does not have dependent sources to include in your experiments. So you're not gonna see that. But in general, we connect here the negative terminal. You connect it to the negative terminal of that voltage source, right? Now the controlling variable here would be basically the current into this branch. But as a voltage, you connect the negative terminal of the dependent source to the negative terminal of the 10 volt that is already connected to those resistors. So that's what you do. Negative terminal to the negative terminal. This means that you have now a common reference point. Does this answer your question?
I'm still a bit confused. Like, at this point here, a current should split.
No, no, the current is not gonna split. The current is not going to split.
And why is that? Because usually that's what happens at a node, like at a junction point.
Now, for this IS, the current is going to see a shorter path between the 10 volt here. So let me show you. This IS is going to go from the voltage source all the way and come this way, then it will be going in this direction to control to close the path more than going this way. Why? Because if you look at this one as a zero voltage, right? This one is here, the voltage drop. You don't have a closed circuit here, but you do have a closed circuit here.
Oh, so because it's a ground node, essentially, it has 0 volts and therefore almost no current. Well,
But
basically
no,
zero
no,
current.
no. You cannot look at it this way. You cannot look at it this way. What you need to look at here is a closed path for the current. This one is a closed path for the current. Here you have a closed path. Okay. Here you don't have any path that basically this voltage source is forcing the current to come back to it. But here in this case, you do have a closed path. This one, it's an open path. This one is an open path for the current. It's not gonna go this way.
And so
And
why doesn't
and the
it go that
same
way?
and the same applies for I naught. Look at I naught. I naught is gonna go this way. Because that's the closed path for I naught.
I mean, it's what's stopping them connecting to that branch there.
There is you look at the voltage source as a pump, right? As a pump, creates pushes the water to go in one direction and at the same time pushing it to come toward it. Here, here in this case, there is no closed path that basically forces the current to go in that direction. The only thing that this is doing is creating the same potential between this and this. Look at them as two separate circuits. They're two separate circuits that are sharing the same potential. What is connecting them, what is binding them, is the controlling variable, which is the IS. So this is what the source is doing. The source is pushing the currents to go in one direction, and at the same time attracting the current. If it's here, for example, this 10 volt across the 6 ohm, the 6 ohm is the only closed path. The 6 ohm is the only closed path that this current is seeing, generated by the 10 volt.
Is it because of the potential difference? I mean, you need that to create a closed path because ground is 0 volts.
Now, tell me what's going to happen. So let me ask you this. What is going to happen if I break? Let me now clean up this whole thing. Now we understood what happened. But let me ask you this. What's going to happen if I come and break this circuit?
It's just one mesh or loop here.
What's going to happen to IS?
Gonna remain constant because it's only gonna going for that loop.
If I break my circuit here?
Oh, well, it falls to 0
Why did not continue go?
because you
Why did
broke it
not continue going from the 10 volt and taking this path?
because you broke the circuit.
Because I broke the circuit. So at the end, what we're seeing is two separate circuits, two completely separate circuits that are sharing the potential at this node and binded by this controlling variable, this controlling current, right? So IS is going, in other words, IS is going this way, and I naught is going this way. Now, if I break this circuit, look what's going to happen. If I break this circuit here, IS is going to be, you just said it,
0.
0. Now, if IS is 0, what's going to happen to I naught?
If you break sorry, say that again.
If I break this circuit here, you said that IS is going to be 0. And that's correct. But what's going to happen to I naught?
Well, if it's a separate circuit, it doesn't have an effect
But it will be 0. Can you tell me why?
because you basically created an open circuit then.
Because IS is 0. So the potential difference now across this dependent source is 0. That's the link between those two circuits. So physically they are separate and sharing this potential, but they're still binded by the controlling variable. Does this make sense?
I think so, yeah.
Okay. Now, if I break If I break this circuit without affecting the first circuit, I naught is going to be 0. But is IS 0? No, that's correct. Do you now understand the connection between those two circuits? Is the link now clear?
Still a bit confused, but we should move on.
Okay. As I said, they're sharing the same reference point here. So if I put this one to ground, I have the same node here. But the current is based on the resistor here. IS is based on the 6 ohm that is going, that this 10 volt is going across. And then after you find this IS, this voltage source will be dependent on this IS. Now let's go and continue solving. Things will become, I guess, clearer. So we found IS because 10 volt is across the 6 ohm. After we found IS, and we found, now we can find this voltage. Let me call this one as VP, just VP, and this VP as 3IS. So VP as a 3 times 1.667, and VP as 5 volts, right? Now I need to find V naught. How can I find V naught? Can somebody tell me how to find V naught? I found now this voltage, VP. If I write the KVL here, what do I have? Minus VP plus 2 I naught plus V naught equals to 0, or V naught as VP minus 2 I naught. Right? Now, how can I find I naught? I know VP. I'm missing I naught. Do you know how can I find I naught? Or, by the way, instead of writing V naught, so this is one way. A second way is, instead of writing V naught, KVL at L1 minus VP plus 2 I naught plus 3 I naught equals to 0. Then I have 5 I naught equals to VP, right? Or I naught is VP divided by 5. I naught is VP is 5 divided by 5. I naught as 1 ampere. What about V naught? Look at the relationship now. V naught is I naught times the 3, then V naught as 3 times 1, V naught as 3 volts. Okay, so this is how we found V naught. If you want to do the power, then if you want to do the power, then you can say for the 6 ohm, 6 times the current IS, which was 1.667 squared, 0.667, 16.67 watts. This is the 6 ohm. The 2 ohm is how much I naught? I naught was 1 ampere. So we have here 2, 1 squared is 2 watts. P 3 ohm is 3 is 3 watts. Right? Now P for the 10 volts is 10 times IS. Negative, right? Why? Because IS is entering minus 16.67. The PP or VP is also I naught as entering the negative. So I'll write it as minus I naught is 1. VP as how much was VP? 5 volts. Minus 5 watts. Supplying. So if you put now sigma power, we have 16.67 plus 2 plus 3 minus 16.67 minus 5. It's obvious that sigma p is 0, right? Any question about this problem?
Sure.
Yes.
So if two loops are connected by just one wire that's essentially ground, then we just treat them as two separate loops. Is this
Yes.
always the case?
Yes. Now here, this is an example of this. Now, if I have a wire or a resistor connected here, then things would become different, right? Is this clear now to you?
Well, now you've created two connections. If there's just one
Now they
wire,
no, now they became one circuit because now it's not an open loop anymore. Now you have a closed circuit.
what I mean is it's an open circuit if there's just one wire connecting them, and that goes to ground. You add another wire, it closes the circuit.
I picked that wire to be the ground. I picked I decide on the reference point. So not necessarily because it's the ground matters. Not
So,
necessarily because it is the ground.
so it's is it more just it's just one wire and therefore it's an open circuit,
Con-
or
co- Connecting a wire between 2 points of a circuit will make them share the same potential. That's it. But it
okay?
doesn't mean that those two circuits are one circuit.
Well, those two circuits only become one closed circuit if you add another wire with a resistor.
Absolutely. Yes. Yes. This way you have a closed path between the negative terminal and the positive terminal. Although it's going through more complicated circuit, but now you have a closed circuit. Yes, you're right. But right now there is no closed circuit. There is no closed path between this voltage source and this circuit. And the same for the dependent source. Okay, so let's move on, trying to solve as many as we can with all the details required. This is applying series parallel simplification to find the currents everywhere. So in this case, what do? You just simplify the circuit to find the current everywhere. So the first step you probably can do is 3 and 6 are in series. That's correct. Makes it 9. And then this 9 and 18 are in parallel. So we can say that this is going to look like this. So here I have 9 ohm. You can probably call this one, if you want, R equivalent 1. And the current is I2. Here I have 18 ohm and the current is I1. And then I have here 4 ohm with a current being IS. 120 volt. Then we can continue simplifying this circuit till we find IS, which means I will have now those two resistors in parallel. 4 ohm IS. And now this is going to be our equivalent to where I have 6 and 18, 9 and 18 in parallel with a total resistance now of 6 ohm. Now I can find the current IS. Now IS becomes 120 divided by the total resistance. This 120 is across. Again, Another mistakes may be done by students is calculating IS, saying IS is 120 divided by 4. This is wrong. And we have seen now why it is wrong. Because you've ignored the 6 ohm. This 120 volt is not across the 4 ohm. This 120 volt is across the 4 ohm and the 6 ohm that is in series with it. Right? Look at the 120. Look at 120 volt. It is across the equivalent resistance of 4 and 6. So it is divided by 4 plus 6. And now IS. Yes, Matthias, go ahead.
So you need the resistance of the entire loop to create the full 120-volt drop. Like, you're only getting a fraction of that across the 4 ohms. The rest is dropped across the other resistances,
I
or
should
they're
not.
equivalent.
Yes, I should look at the total resistance this 120 volt is seeing, which is 4 plus 6 in series, right? So this is how I find IS. So this is IS. Now, after I found IS, what I need to do, I need to go now backward by finding now the voltage across the 6 ohm. I'm calling it V2. Why? Why I'm doing this? I'm doing this because V2 across the 6 ohm is this one as well. V2 across the 6 is across the 9 and 18 that are in parallel. But I'm taking advantage of finding IS because now I can say that V2 is IS times R equivalent to, and V2 is 12 times 6, right? V2 is 72 volts. Now I know V2. Now I can find I1 and I2. So I1 is V2 over 18, and I2 is V2 over 9. Okay? So let's move on to the last question. Actually, it's not the last one, but I'll skip problem number 4 because we've done several power dissipation. I'll let you do this on your own. And I would like to go to the last one, which is the current division. This is an interesting problem that we can apply the current division with the way, and the voltage division with the way we have seen earlier. So let me start here. When I want to calculate the current I naught using the current division and use the voltage division to find V naught. So the first thing I would do is to simplify the circuit and go to the conductance. We have seen why. And the conductances would be very way easier to apply to use the current division. I'll show you. So here I have one, two, three, and four branches with a current source here, 8 ampere. So the first one is 36 plus 44 is 80. Second one is 10. Third one is also 80. Last one is 24. Now all those are ohms, right? Ohm, 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 and ohm. What I'll be doing is, in order to calculate I naught using the current division, I will go to the conductances, which means I will use the inverses to find the conductance. So this is the current. Why? Because we've seen in the conductance it's way easier to use in the current division. So the conductance here, 1 over 80, is 0.0125. Or maybe I can put I'll, I will put G1, G2, G3, and G4 and calculate those G's here. I have G1 equals to G3 equals to 0.0125 Siemens. I have G2 as zero point 0.1 Siemens. I have G4 as 1 over 24, 0.042 Siemens. Finding I naught using the current division, using the conductances would be I naught equals to, the total current is 8. The ratio, G4 over the total conductances plus G1 plus G2 plus G3 plus G4. So this is the ratio using the conductances. See how easy it is. So I naught as 842 over 0.0125 plus zero point 0.1 plus 0.0125 plus 0.042, then 0.0125 I naught as 2 ampere. And to be precise, 2. So this is, so that's it. This is how we calculate the current division. So this is what I wanted to show you. The voltage division here, now after we found the voltage division, you need to calculate the current here. And let me call this one I3. Use the same method, I3 as 8, right? Which is 0.0125 over 0.0125 plus zero point 0.1 plus 0.0125 plus 0.042. Calculate I3. 0.6 ampere. 0.6 ampere in this branch. If you multiply it by 80, you get the total voltage, right? Times 80, you get the voltage 48 volts. So here the voltage V2 point 6 times 80. V2 is 48 volts, right? Now 48 volts, you need V naught, which is a portion of it. So here V naught as V2, the ratio, what's the ratio? 30 divided by 30 plus 10 plus 40. So V naught is, what's the ratio? 30 divided by 80 times 48 is 18 volts. Okay? Any question? Yes, this is current division. And that's, yeah, Siemens. The unit for the conductance is Siemens. Any question about this problem?
Sir,
So
what did you get for uh, uh, I3?
I 3.6 ampere.
Okay, thank you.
You're welcome. I have it here. Any other questions? Okay, great. So this was a review for our uh, quiz number one. The Y delta transformations. We did not solve any question here, but it is still part of our quiz one material. So if you have any question about it, and I suggest that you try solving several questions by yourself and see how you're doing. If you have any question, we have an office hour on Friday. If you cannot attend the office hour, please let me know. Quiz 1 again is on June 17th, next Thursday. Next week, Thursday, is our quiz number 1. And it's worth 10%, if I'm not mistaken.
I thought it was worth 15 or 20, depending on how you did on the third midterm.
That's correct. That's correct. Yeah, I included in a second option. Yeah.
So, sir, what are we doing this coming Thursday and next Tuesday then?
We're covering regular material. I think, yeah, next Thursday we'll be starting the operation amplifier. Okay. So, if you haven't started studying it, that's the best time. I think we've done it, uh, earlier, such that it's, you know, alerting you to start if you haven't started and to give you time. So, go through the material, solve the questions, attend the office hour. Again, if you have any problem attending the office hour, please let me know. I want you to have the enough time to practice and be prepared for the quiz. So let me know if you have any question. Okay. Thank you and have a good day.